Yeah, so thanks for the kind introduction and for the warm welcome. Yeah, I think I'm the only natural scientist in this term. So it's a bit of a change of gears from last lecture. So I want to talk about paradigm shifts in physics. But because this is a lecture series, I thought I'd briefly pick up the thread from what we learned last week. And we had 2 weeks ago, we had this talk about paradigm shifts in linguistics. And the view on paradigms and paradigm shifts was very different from my physics point of view. If I understood the speaker correctly, he almost defined a paradigm as something that the majority does. So it's something that the majority can also force upon the other practicing scientists. And in his view, paradigms are not necessarily linked to progress. So he observed that there is a recurrence of paradigms within linguistics. So things can come back. So it's not entirely clear whether a new paradigm always represents progress in terms of accumulating knowledge. So as I said, in physics, we have a much more positive, maybe much more naive view of paradigm shifts. And I think it's primarily due to the fact that physics is a topic that Thomas Kuhn used to invent this theory. So it naturally is much more adapted to that. And I want to start with a quote. So Kuhn is the most influential philosopher of science, I mean the most widely read, and to some extent believed by practicing scientists. And for scientists, we can think physicists, really. So that's already a good starting point. If you want to have a theory about what some people do, if those people believe it themselves, that's probably a good sign. So here's the outline of my talk. I want to give some brief remarks on progress in science, question mark. Then I'll start with the general framework of Kuhn, and then we'll go through, in the main part of my talk, through 2 examples to see whether that general framework fits to those physics examples. And then finally, we'll do a quick check, coming back to Kuhn, whether we really think this is a good description of what goes on in physics. And we'll finish with some discussion. So progress in science. I want to start with a naive view, which is quite well represented by this quote by Newton. If I've seen further, it is by standing on the shoulders of giants. So Newton, I think, originally mainly used this phrase to show his modesty. But by unpicking what he actually said, there is an underlying view of how physics or science makes progress. So let's look at the key terms here. I have seen. So that means there is actually some truth out there that we can discover in physics, and that's what we're trying to do. The second keyword here is further. So science can go further. We can make progress, and we do believe that we add to the knowledge of our predecessors. And finally, the standing on the shoulders of giants is a way of describing on how this progress happens. Yeah? So progress in terms of physics knowledge happens by adding new knowledge to the existing knowledge. So if you want to use a metaphor, it's almost like building a tower that gets ever higher. And it's a process that goes brick by brick, incrementally. So Kuhn came along. Kuhn is a historian or philosopher of science. He was a physicist by training. And he wrote his famous book, The Structure of Scientific Revolutions. And his central thesis is that this naive view is not right. Progress in science is not a gradual process, but instead scientific progress makes jumps. And in order to understand this, let's start with a provocative statement that he made, and that's basically a bit of an insult to all practicing physicists. The scientific enterprise as a whole does from time to time prove useful, open up new territory, display order, and test long accepted belief. Nevertheless, the individual engaged on a normal research problem is almost never doing any of these things. So these are the things that we as physicists think we're doing all the time, and Kuhn says, no, that's not what you're doing. And here's why. So the scientists that he referred to were the scientists that he calls normal scientists. So as I said, Kuhn's central thesis is that progress doesn't grow continuously, but it makes jumps. So if you have jumps in between, you will have stages where there's not much going on. And that's kind of all of us normal scientists. And the normal scientists work within an existing paradigm. So let me briefly introduce what he means by paradigm. So in his, and there are, I think, about 30 different ways of using the notion paradigm, even within Kuhn's original work. And I'm going to use the kind of the most extensive meaning, where a paradigm is a disciplinary matrix. So it's kind of the set of how a discipline works. And it consists of several components. We have what he calls symbolic generalizations. So these are the fundamental laws of nature of that field and how to interpret them. We have metaphysical beliefs. These are the underlying philosophical assumptions that have to be used with those laws of nature. We also have a set of values, and by values he means how we decide whether a new result or a new experiment is correct or a new theory. So it's kind of a system of criteria on how to judge the quality of new work. And then this is the most explicit use of the word paradigm. It also refers to, paradigm means example. So a paradigm also includes exemplars, so example problems and solutions, key experiments that others have repeated, or key problems or key theories. And that's the part of a paradigm that's most obvious, I think, to practicing physicists, because that's what you learn when you go to university. Yeah? So you attend a lecture, and then a major component of a physics education is also to sit in small tutorials and solve problems and do problem sheets. And then you will notice that if you kind of work in a certain field like mechanics or electrodynamics, there's always a certain way how these problems are set up. And that's what's meant by these exemplars. So that's what's going on when we have an existing paradigm and scientists just keep working within that paradigm. That's kind of the what of the jump. So the next question is, how does it jump? How do we get these shifts in paradigm? And there we come to what Kuhn calls extraordinary science, or scientific revolutions. And he gave us, being a historian of science, he gave us an order in which certain steps occur in order to make progress. So we have normal science, a steady extension of knowledge, adding some detail to a paradigm, not much progress going on, just some further tiny new facts. And then there will come a point where the paradigm has kind of stretched its scope. And then you will find some new facts that don't really fit within this paradigm. And initially that doesn't get noticed by many people. But eventually, if we get more and more anomalies and they don't go away, even after many theorists or experimentalists have tried their hand on solving those, we come to a state of crisis where the majority of the field thinks there is a problem with the existing paradigm. In that stage, there will be a questioning of the paradigm, and there will be lots and lots of different ideas, lots of discussions going on. Everything will be questioned in order to overcome this crisis. At the result of this, in the very end, we can have a scientific revolution, which is the establishment of an entirely new paradigm that will then become the paradigm of the field. The important feature here is that the new paradigm is often incompatible with the old paradigm. So if I come back to my tower analogy, we used to say, okay, progress in science is like building a tower brick by brick. So if you say it jumps, it could be a tower that you build level by level, one level at a time, not tiny bricks, but really big steps. But what Kuhn says is really something completely different. We build a tower, we abandon it, and build something completely different somewhere else. So that's the central part of this thesis, that he not even does it make jumps, but it also kind of sometimes means that you have to discard what you knew before. It's incompatible. So in order to make further sense of this, I have picked two examples, which were the two prime examples that Kuhn used to come up with this idea in the first place. The two main scientific revolutions of the 20th century. And the first one is the shift from Newtonian mechanics to special relativity. So I see that the majority of you are non-physicists, so don't be afraid. I have almost no formulas on here, and I won't try to explain all the physics to you, but just enough that you can appreciate how this is a paradigm shift. So Newtonian mechanics is all about how objects move. So the primary quantities that we have within that paradigm are space and time, and they're considered to be independent of each other. I can see where something is, and I can see when I observe something, and it's pretty much independent. And also, the length of an object and the duration of an event are independent of what the observer does. So if I want to measure the size of this bottle, and I take my time and take a measuring tape, and I do it properly, I'll get the same result that I would get if I kind of ran past the bottle, did a quick measurement, and just moved on. So the length or the height of this bottle is a quantity that's inherent to the bottle. It does not at all depend on what I do with it. Yeah? Same thing with time. And so if you have length and duration, then you can calculate velocities of things. So that's kind of the length that an object passes divided by the amount of time that it takes. And that's a property of the object. That's something that can change. If I speed up the object, it will have a different velocity. And then finally, velocities can be added like numbers. So if I run at 15 kilometers per hour and I throw a ball at 50 kilometers per hour, then the ball will have a speed of 65, if I'm not mistaken. Yeah? And that's actually something, it's a paradigm of classical mechanics, but it's deeply ingrained in even in our subconscious thinking. So anyone who plays ball game of any sorts, for example, if you play basketball, you make a jump and then you throw and try to kind of hit the ring while you're in the air jumping. Your brain implicitly takes into account that you already have some motion to start with some velocity, and you have to adapt your throw to what you would have done if you were just standing still. So that's what makes this a paradigm. It's so deeply entrenched in our thinking. And so I said a paradigm has model problems and solutions. The typical physics problem sheet problem that first-year physics students will do is determine the trajectory of objects under the influence of given forces. So for example, calculate the motion of a planet around the sun, calculate the swinging of a pendulum. So that's the typical kind of task that a mechanics person has to solve. So that was the existing paradigm. Let's come to the new paradigm, special relativity. And as I said, in order to have a new paradigm, we first need to have some sort of crisis. And I've picked two indications of this crisis of classical mechanics here. Firstly, there were experiments trying to measure the speed of light. This only became possible quite recently because light is so very fast. And then basically, people tested this idea that if I run and I throw something, that thing will fly faster, because it gets this additional velocity that I had. If you try the same thing with light, so you run and you shine a beam of light, you would think that then the light would be faster, right? Because you gave it an additional push. And people tried this in experiments, and it turned out that light isn't faster when you run. So the speed of light seems to be a universal quantity. It doesn't depend on how you look at it, and you can't change it by kind of speeding up the source. And that also led to an observed deep contradiction between mechanics and electromagnetism. Electromagnetism is the theory that describes light, and mechanics is what I just described. So the two seem to be incompatible. So in this case, this crisis was single-handedly resolved by a single person, Albert Einstein. And he gave us this new paradigm of special relativity. So let's just look at what that new paradigm means. We used to have space and time as the primary quantities. Now the most important primary quantity of the new paradigm is the speed of light. And the speed of light must be constant no matter what I do. And everything else has to fall into place to make sure that this is still true. So then, an immediate consequence of that is that length and duration depend on the state of the observer, on the reference frame. So if I measure this bottle and I stand still with the bottle, I will get a different result than what I get if I run past the bottle and try to quickly look how long that bottle is. So the length or the size of an object is no longer an inherent quantity that doesn't depend on how I look at it. Also, space and time become very much interdependent. So if I have a spatial distance between two events and I move between them, I can transform that into a time difference. And finally, and that's maybe the most surprising fact here, is that we get a non-trivial addition of velocities. If I move with a certain speed v and I add the velocity of light, the result that I get is not v plus c, the result is c. So it's a very funny way of adding numbers. Also, if I add c plus c, the answer is not 2c, but the answer is again c. So let's come to the typical problem that people would solve within special relativity. So instead of just determining a trajectory, we now have to determine the properties and behavior of objects under the influence of forces given a specified frame of the observer. So that's an obsession that you have in special relativity, that you always have to think, if someone asks you, tell me how is this object moving, then you always have to ask him, tell me first how I'm moving. Yeah, so it's always relative. You always have to make sure, or you always have to declare whether you stand still in the auditorium or whether you're moving yourself. And it should be pretty much clear that we have some strong incompatibility here of the old and the new paradigm. The length of an object used to be independent of the observer. Now it's a quantity that can change, so that's completely different. Same thing with time. Also, a surprising consequence is that within special relativity, there's no such thing as a rigid object, because nothing can move faster than the speed of light. If I have a long pole and I move it, then kind of the motion that I have here will move to the other end of the pole with a very great speed that would violate this requirement that everything has to be slower than the speed of light. So that's something completely unexpected that comes out of the paradigm. Yeah, everything was about just motion of objects, and now all of a sudden we get a new insight into how objects can behave. Okay. So let me come to my second example. That's the second major revolution in the 20th century, the change from classical mechanics to quantum mechanics. So the starting point is pretty much the same. So in both cases, we start from classical mechanics, but we change different aspects of that theory. So let me just reiterate what classical mechanics is about when we look towards moving to quantum mechanics. So in classical mechanics, as I said, primary quantities that you can determine would be position and possibly velocity. And they're pretty much independent. An object can be here or there, and that doesn't depend on whether it's moving or not. I can be here and moving. I can be there and not moving. That doesn't have any obvious relation. And also what's deeply entrenched in classical mechanics is the belief in determinism. So if I know the motion of an object here and now precisely, I can determine its fate forever. I can completely predict where it's going to be in 10 seconds, in 1 hour, in 1 year. So that even went so far that the adherents of mechanics believed there can't be any free will, because everything is basically mechanic objects, and everything is predetermined. If I know the state of my brain now, I know exactly how it will evolve So it's a very much a philosophical issue as well, if you believe in that. So what's the role of chance? Chance is only a way of saying that we haven't done things properly. So if we can't predict things completely, it only means that we haven't looked properly what it's doing now. Or maybe we can't for some reason because it's too small. But it's not an inherent problem. It's just that our knowledge, because we didn't make enough of an effort. So here's again the typical problem. We define, we say we know the initial positions and velocities of things, and then the task is to determine what these objects do in 10 minutes or in the far future. So again, there was a crisis that ultimately led to the invention of quantum mechanics. In this case, I picked two of the elements that led to the crisis. First one was a puzzle, which was the unexplained stability of the atom. An atom in a classical world is a positive charge, the nucleus, and some electrons going around it. Now, electromagnetism says that if I have a charge that moves in a circle, it will emit radiation, so it will emit light. And then energy conservation tells you that if something emits light, the energy has to come from somewhere. So that means the electron will have to lose some energy. It will have to slow down. And as it slows down, it will slowly fall into the core. Yeah? Just like, I don't know, an asteroid falls onto Earth when it loses energy in the atmosphere. So it means that ultimately no atom should ever exist if we wait for long enough, because all these electrons would have fallen into the core. And the other puzzle came from an experiment, which was to poorly understand properties of black body radiation. So that was a theoretical construct, kind of the perfect object that would radiate. And if you look at how this object emits light at different colors and frequencies, the observed properties couldn't be understood or explained properly. So in this case, there's a couple of, or a bit large set of people who contributed to this scientific revolution. So we have a lot more of this typical debate going on. I would say if we had to name a few, it would be Niels Bohr, Heisenberg, Schrödinger, Dirac. Don't know if I forgot anyone. And so the new paradigm is, instead of looking at position and velocity of objects, we now look at the energy and the wave function of an object. The wave function is a strange object that can be used to predict probabilities of measurement outcomes. So instead of everything being completely determined, physics now becomes a lot more modest, and we just say, we can't say where this is going to be, but I can tell you there's a 50% chance that in 10 minutes it's going to be there, if you look. And also there's what's called the uncertainty principle, which says that position and velocity can't be measured at the same time. You can't even determine it for principal reasons. So this incomplete knowledge is no longer our fault. It's a principal feature of the theory. So the typical problem is no longer, let's determine where this object goes exactly at every point in space and time. But instead, an undergraduate quantum mechanics student would have to determine the energies and wave functions of a certain system, which he can then use to predict the outcomes of measurements. And here we have a very marked incompatibility. So what they used to do in classical mechanics to determine a trajectory is not even possible anymore, because there is no trajectory. We can only say there is a certain probability for objects to be here and there. We also have the principle of complementarity, which says that, or which implies that the results that you get will depend on the questions that you ask. You can say, I want to know what is the speed of this object here. You can say, I want to know where it is, but you can't ask the same question, those two questions at the same time. So the answers that you get very much depend on the questions that you ask. And then also we have the phenomenon of entanglement, which is a contradiction with classical probability theory. So even if you admit, OK, everything is random and we can't really determine things, if you try to describe this with the normal with your intuition for, say, rolling dice or anything which is probabilistic. There will be cases that you won't understand if you don't do quantum probability theory. Okay, so I've shown you these two examples, and I thought we'd just briefly come back to the general framework and have a quick look at whether these features of a paradigm really apply to these two examples. And I'll try to do this fairly quickly. So in order to have a paradigm shift, we need to have a crisis. And I think I've convinced you that in both cases, relativity and quantum mechanics, we had a very clear crisis that was perceived in Einstein's case mainly by, or solved by a single person, but perceived by many. And this, in the case of quantum mechanics, similarly perceived by many, I guess. Then the question is, did we really change the four aspects of the paradigm? So did we change the laws of nature? It's a clear yes for relativity and for quantum mechanics. Underlying philosophy, I think, is a very clear yes for quantum mechanics. If everything is random, that's a very different world from what you believe in if everything is predetermined. And it's also true for relativity, I think. Values, it's also a completely different set of your values for judging what makes sense and what doesn't. So in classical mechanics, if someone came, oh, I've solved this problem, but I can only give you probabilities for whether things happen, he would say that's not a good work. But in classical mechanics, in quantum mechanics, that's all we can do. So the values for whether some solution is good or not has completely changed. Similarly, in relativity. And I also try to convince you that the kind of problems that we solve are also completely different. Finally, incompatibility for quantum mechanics is a very clear yes, because the kinds of questions that you ask, the whole picture has to be discarded from classical mechanics. In the case of relativity, it's a bit of a maybe, because if you go to low velocities, so if you don't go to the speed of light, you will recover that classical mechanics is still a good description. So you don't really kind of have to abandon your whole tower and build something else, but there is still some aspects of the old paradigm preserved. So I want to finish with some discussion points. So I think the first question that one obviously has to ask is this a good description? So is Kuhn's description of physics progress in terms of scientific revolutions, is it accurate or not? And in particular, one can ask whether there can also be cases where we have progress without having to have a scientific revolution, without having to overturn everything. One can, of course, also ask, as was asked in the previous lecture, whether a scientific revolution always is progress. Maybe we abandon our old theory and we come up with a completely new one, but maybe that's not really necessarily better and we have to return to the old one at some point. And then finally, from my first quote of Kuhn, that's a very negative view of kind of 99% of all the physicists, because most of us are not so fortunate to be the creators of a scientific revolution. So the first question would be, is this description still accurate? So do we just have to admit that we try to be really useful and inventive, but maybe we just aren't? And if we think that's the case, then of course the next question would be, is that what we really want? And do we need to change the way we're working? With that, I almost like to close. Just some further reading. I think every one of you who's never read this monograph by Kuhn, The Structure of Scientific Revolutions, I think it's really it's a very good read and a good idea for many fields in science to kind of get an idea or have some framework for how you think science progresses. Even if you don't agree with it, you've thought about it. And the second one is how I came to read Kuhn. So I once had to write an essay on what Kuhn tells us about the use of philosophy in physics teaching. I think I'm going to post this on the abstract announcement page of this talk, if you're interested. So just very quickly, this is going to be next lecture in 2 weeks' time, and it's going to be about paradigm shifts in politics or political theory. And with that, I'd like to thank you and open for discussion. Thank you. Thanks.